minus 2y is also positive. Now, which means you're changing the domain of a function a lot.
Right.
So the function is fundamentally a different function anymore. It's not going to be the same function, right? So we're going to prove this is not going to be existing. So one observation I want to give you is to look at a graph. So if I have a graph of function, so this is the given fixed point in the xy plane, okay? So coming back to the definition of a limit, says if the limit of a function is equal to L when xy approaches AB, which is saying if your input xy is very close to this fixed point AB, then the function value when you go back to the graph will be very close to this level L. Are you with me? So xy's are coming from a small neighborhood of AB. So the limit of a function exists at this given point is saying as long as your xy approaches this point, then the function value will approach this value of L. All right? However, there's a big problem of what we define by approaching. If you're on one-dimensional line, approaching a given point is pretty easy. You can approach this point from right, you can approach this point from left. But if we're approaching this fixed point AB on the xy plane, you have much more different choices of approaching. Am I right? You can go from the parallel line of x-axis to this given point. You can go a parallel line of y-axis to this point. Am I right? You can go this direction, which is parallel to y-axis. You can also go this direction, which is parallel to x-axis. You can even go zig and zag to this point. You can go any imaginable curve as long as it is getting closer to this fixed point AB. Basically, on the plane, when we say approaching, when we have these neighboring points approaching a fixed point AB, you have much more different choice of paths to go to approach this point. And with me, much more than if you're on the one-dimensional point, one-dimensional line. If you're on one-dimensional line, you can go to this fixed point from the right and from the left, and that's it. But for two-dimensional plane, you can go to a fixed point from different paths. Okay? Now, if the limit of a function exists at this given point, it is essentially saying no matter how I approach this fixed point, no matter which path I choose, then the function value will always approach to the same fixed value L. I'm going to say it again. If the function has a limit at this given point, then no matter which path I choose for xy to approach to AB, I should always converge to the same value L. All right? In other words, the way of approaching AB should not affect the convergence. Yes? I should always get the same value as my limit. In other words, again, if I want to prove this limit does not exist, as long as I can find two different paths and approaching this same fixed point from different paths going to be two different values in the end, then the limit is definitely not going to be existing at this point. Are you with me? So proving the limit of a two-variable function does not exist at a given point, the only thing you need to know is to find two different paths where you can get two different limits. Okay? So if we have path 1 and path 2, so you need to choose two different paths for xy to approach AB. And then these two different paths, when you plug into the formula, you're getting two different limits. Then this will be enough to guarantee the limit does not exist. Okay? So we're looking at this function again. I'm looking at the neighboring points x, y, and I want this xy to approach to 0, 0. Again, there are two very trivial paths you can choose. One is through x-axis. The other one is through y-axis. What do we mean by x-axis?
Direction parallel.
Y equals 0. So if I want to approach t, the fixed point to be 0, 0, I want xy to be equal to y is equal to 0 and x is a new variable which is approaching to 0, all right? So if I fix x to be 0, I let I'm fixing y to be 0, I let x to approach to 0, then this whole point will be approaching to 0, 0, am I right? Goes to 0, okay? So when we say a path, we're actually fixing one of the variables and let the other variable to vary. So this is gonna be a path rather than a plane, all right? So as t goes to 0, this is the one path you can choose for x, y to approach to 0, 0. And then I can plug in this particular formula of a path back into this fraction and see what the limit is. But right now, the limit is much easier because in the very beginning, my limit is about x, y approach to 0, 0. By fixing onto a path, now I'm looking at the limit as t goes to 0, okay? So if I plug in t0, I'm getting a limit t goes to 0, x is equal to t, y is equal to 0. I'm getting a 1 in the end. So this is a constant function 1. When t goes to 0, the limit is still 1, am I right? So this is the limit when t goes to 0 of a constant function 1. So in the end, I'm still getting a 1. Okay, so this is the limit of a function which is restricted on a path where y is constantly 0. You can similarly choose a different path where you fix x to be 0. And that path will have the formula xy is equal to 0 t. As t is going to 0, this path will also converge to 0, 0. As t goes to 0, this path is also converging to 0, 0. So I can plug in 0t in this fraction and try to compute the limit, not as xy goes to 0, 0, but as t goes to 0. So it's essentially a one single variable function limit, okay? So we're looking at limit t goes to 0, 0 plus 2t minus 0 minus 2t. So in the end, we're getting a limit of negative 1, all right? So this is a constant function. When t goes to 0, the limit of a constant function is still minus 1, all right? So two different paths gives you two different limits. Then this fact alone will be sufficient to justify the limit does not exist, okay? So these two are different. So you can say limit as xy approaches 0, 0 of x minus plus 2y, x minus 2y does not exist. Again, I want to briefly justify why this fact alone will be sufficient. If this limit exists, then regardless of what path you choose, you should arrive at the same value, am I right? But because you're choosing two different paths, you're arriving at two different values, then this limit has to be not valid. You know what I mean? So this fact alone will be sufficient. Okay?
So you're saying that for the second example, the one we did with the algebra, if we were to actually try to see if it didn't exist, we did the two paths, they would both equal each other? Okay.
However, if you want to prove the limit exists from a path argument, it's not going to be easy. Right? Because you have to choose all the possible paths. But there are a whole zillion of different paths you can choose.
Okay.
Proving it does not exist from the path argument would be significantly easier. Because as long as you have two different paths with two different values, you're done already. Am I right? If you want to prove the argument from the path for this particular example, choosing two different paths, you're arriving at the same value does not say anything. Right? You have to go for the third path, first path, and all forever, which is not friendly to work with at all. I would think. So that's why we didn't go for that argument. So the path argument will only be easy to use if the problem is to prove the limit does not exist. Okay, so never use this argument unless it's asking you to prove it does not exist. Okay, so let's look at a couple of more examples. So I want to look at the limit x, y approaches 0, 0, y4 minus 2x squared y4 plus x squared. Okay? So this is the example we have. Again, if you plug in 0, 0, the denominator vanishes, so this is not in the domain anymore. We cannot use continuity argument. Okay? And we want to show this limit does not exist. Okay? Again, I'm not going to give you the problem where the point is not in the domain and you prove the limit is equal to whatever number. You only need to verify the limit does not exist in the case where the fixed point falls outside the domain. So immediately as you see this kind of problem, what do? You design two passes and always begin from the easiest one. Okay, always begin from the easiest one. As I said, there are different ways of designing the passes, but the easiest ones, especially if the points are approaching 0, 0, will be t0 as t goes to 0. This is approaching the origin from x-axis, and t0t as t goes to 0. This is approaching the origin from y-axis. So these are indeed two different passes. Okay. So from the first pass, we can plug in this fraction. What do we have? So it's limit t goes to 0, y is equal to 0, so I'm getting a 0 minus 2t squared, all right? The denominator is going to be 0 plus t squared. So still we're arriving at a constant function minus 2. When t goes to 0, it is still equal to minus 2. And second case, if I'm plugging in x equals 0 and t is equal to y, we're getting a t to 4 divided by t to 4, all right? So we are arriving at a different value indeed. So it is equal to 1. Two different passes, you're arriving at two different limits. So this limit does not exist, okay? So usually, if you look at these fractions, begin from x and y, two different passes. These are the most trivial ones. You can begin from this one and check if you're arriving at two different values indeed. If this is already done, then the problem is proved. So here is another question I want to ask you. Let's say if I have a function, I want to prove this function does not have a limit when xy approaches a fixed point. I'm choosing a path coming from x-axis or parallel to x-axis. I'm choosing another path coming from y-axis or parallel to y-axis. Both of these two passes, I can compute the limit and arriving at exactly the same number. What do? So when you prove the limit does not exist, you design your two passes, but these two different passes do not give you two different values. You have to go and find the third one. If the third one is also providing the same number, you have to find the fourth one until you can find a different path with different limit as the number in the end. Then you will be done. However, most of the problems, you don't have to go that far. Usually 3 passes will be sufficient. And we have the passes of x, y approaches 0, 0. So I will list a couple of very popular passes we will choose from. So first one is t0 as t goes to 0. Second one is 0t as t goes to 0. So this basically is talking about if we want to approach to the origin, we can approach from x-axis. We can approach from y-axis. So these are the two popular choices of two different passes. Can you give me any other path to approach the origin other than the x and the y-axis? You can pass the origin with slope 1, for instance, 1 or negative 1. If we're approaching this origin from this straight line, and the slope with 1 is having the equation of y equals x, all right? Y equals x. So essentially, if I want to introduce one new parameter t, this path is going to be t and t, all right? So this path having the straight line as its graph. So the equation is y equals x, which is essentially saying you need one parameter to make a x and a y are equal, right? So as t goes to 0, so this will be a path passing through the origin as well. You can indeed choose a negative one as your slope. So this is indeed passing through the origin from a different straight line. In fact, you can choose your passes to be very complicated smooth curves. You can choose to be cosine curve, sine curve, whatever. But most of the cases, in order to make your computation easier, what path do you choose? Linear straight lines, all right? So these ones are the easiest straight lines. These ones are slightly more complicated. Indeed, you can choose, for instance, t, 2t. This is still a straight line with slope 2. So this is t goes to 0. In more general case, you can choose t, kt as t goes to 0, where k here is a natural number to define your slope. So you can find any straight line converging to the origin with different slopes. By changing your slope, you can have different passes indeed. And these straight lines as a family usually will be good enough. You don't have to go to very complicated sine, cosine, or log curves. As long as you can select two different slopes, and then usually you will arrive at what you need in the end. So I will give you a couple of examples to practice this principle. So let's say I have a function limit x goes to 0, xy divided by 5, x squared, xy goes to 0, 0, plus 4y squared. Still, I want to show this limit does not exist. Okay? This limit does not exist. Usually, I just begin from the easiest case. Begin from x-axis. So t0 goes to 0, 0 as t goes to 0. So I plug in this straight line as y is equal to 0. The whole fraction will vanish, right? The whole fraction is vanished. So this limit as xy approaches 0, 0 from x-axis will